All right, here are the solutions to lesson 14, 8, and 9. Lessons 14, 8, and 9 for week 7. Here are the graphs for number 1 of F and G. Each represents the height of an object being launched into the air as a function of time. So time is our x-axis, this is our independent variable, and height is our y-axis or dependent variable. So which object was launched from a higher point? Looking at the y-axis here, this is the start of each graph, and so it looks like at 0 time, the green one was launched at a lower point than the blue graph, and so let's see, the blue graph is g, so I would say function g. So maybe we should write that out as function g. And then which object reached a higher point? So let's see. It looks like the green graph reaches a higher maximum up here. So I would say F, object F, maybe that's the way we should put it here. Not function. But they're asking which object, so we'll call it object G up here. All right. And then letter C, which object was launched with the higher upward velocity? So it looks to me like this one, the function f, is going up at a faster speed than this one. And so I would say F, object F again. And then which one landed last? And so this is time along here. So F lands before G. So G is the object that lands last. Number 2, the function h is given by this function of h of t, models the height of a ball in feet t seconds after it was thrown. So we have a function in factored form, and we want to find the zeros of the function. We want to know what they represent. What do they tell us? Are they both meaningful? From what height is the ball thrown? And we want to explain our reasoning there. And about when does the ball reach its highest point? And about how high does that ball go? So we're going to type this into our graphing calculator just the way we have typed in others. So we're going to go over to Desmos, and we'll type that in. And then answer the questions from there. So the function reads h of t, so we could do that. We could go to our keyboard and do h of t, and then get the right one there, and then equals, and we want our left parenthesis here, and it's 1 minus t times 8 plus 16t. And parentheses. And so here's our graph. So we're going to zoom in on it to kind of answer some of these questions. So the first question says find the zeros of the function. So I'm going to kind of bring it down like this. See if I can get this to come out a little bit. I'm just moving my fingers along here to see if I can get it to read better for us. So the zeros of the function are where it crosses the x-axis. So our zeros are at negative 0.50 and 1 comma 0. So negative 0.50 and 1 comma 0. And then they ask, what do the zeros tell us about the situation? So that's when, let's see, this is a ball. So when the ball is 0 feet high. Oh man. So when it has 0, let's write it this way. When the ball has a height of 0. So that 0 tells us the height, and the when is the t, right? So at negative 0.5, that doesn't make sense. So no, negative 0.5 comma 0 does not make sense, is not meaningful. So and then letter D, about when does the ball reach its highest point, and about how high does the ball go. So let's go back over to Desmos. So we want to know when and how high. So if we tap on that very top vertex point, the maximum point of this parabola, it looks like it reaches its highest point, 0.25 seconds, and that high point is 9 feet. So I think I skipped a question here, so I'll have to go back to. So it's 0.259 or 0.25 comma 9, so it's 0.25 seconds. That's when, 0.25 seconds after it's thrown, and 9 feet is the highest point. And from what height is the ball thrown? So when the ball has a height of 0, that's when it's on the ground. So there was only one that made any sense then. That's because the ball was thrown from a height of 8 feet. So this person is a tall person throwing the ball above his head, his or her head. And let's see, at 0 time, the ball is 8 feet above the ground. So maybe this person is on a trampoline or something, throwing the ball up. We don't know. But those are the answers to number 2. Number 3 then. The height in feet of a thrown football is modeled by this equation. So we're going to use technology on this as well. And we want to know, what does the constant 6 mean in this situation? So remember our time height function, h of t. They're calling it f of t here, but that's fine. So h of t is h sub 0, that's the initial height, plus v sub 0 times t, that's the initial velocity, or speed. And then minus 16t squared, that's gravity. So it looks like the constant term is our initial height here, and that's 6 feet. So the ball is thrown from a height of 6 feet. Oops. And what does the 30t tell us? That's the initial velocity. The ball was thrown with an initial velocity of, and then since this is measured in seconds and we're talking about feet, we're going to say 30 feet per second. So that's the speed or the initial velocity. And then how do you think the squared term affects the value of the f? So what does this term reveal about the situation? The negative 16 feet squared is gravity, and that's pulling that object, the football, down. So it reveals that we're talking about something that's being propelled into the air by measured in feet, because that's where the 16 comes from. And then, that's pulling it down at 15 feet or 16 feet per second per second. So that's why it's accelerating. So the gravity accelerates as the ball gets closer to the ground. Number 4, the height in feet of an arrow is modeled by this function, where t is seconds after the arrow, where t is in seconds after the arrow is shot. So when does the arrow hit the ground? That will be when h of t is 0. So let's take a look at that function on our Desmos again. So we'll go over here and type it in just the way it looks. So it's 1 plus 2t. And then 18 minus 8t. All right. So let's take a look at this graph. Oh. Oh, this should be a minus. Okay, that's better. So this is an arrow after it's shot out. So here was what we've got. It looks like it's going from a height of 18 feet to begin with. It reaches a maximum of 30.25 feet after 8.875 seconds. And after 2.25 seconds, it hits the ground. So I'm just going to screenshot this and bring it over to the Notability so we can answer our questions without flipping back and forth. So there it is. So the first question we want to know is, when does the arrow hit the ground? Explain your reasoning. And the second one is, from what height is the arrow shot? So it hits the ground at 2.25 seconds, because that 2.25 comma 0 indicates the height of 0 at 2.25 seconds. And from what height is it thrown? It looks like, or is it shot? It looks like from a height of 18 feet, because at 0 time, the height of the arrow is 18 feet. So the next one here, we've got two objects, object A and object B. We shouldn't have to graph these to answer these questions here. Two objects are launched into the air. Object A is given by this function, and object B is given by this function, g. So which object was launched from a greater height? I would say this one was launched from 2.5 feet, and this one was launched from 4 feet. So F, object F, was launched from a greater height. And letter B, which object was launched with a greater upward velocity? Now we're looking at this number here, the 32 and the 40, so object G. Let's just say object G had greater initial velocity. Number 6, Predict the x and y intercepts of the graph of the function defined by the expression x plus 6. And then we're going to check our prediction. So x plus 6 and x minus 6 from lesson 9, we know that x plus 6, actually we can skip this one because we haven't done this yet. So let's skip number 6. I'll change that on yours so that it doesn't even exist. How's that sound? And we'll move on to lessons 8 and 9 then. So draw a diagram to show that 2x plus 5 times x plus 3 is equivalent to that. So we're going to draw our diagram for multiplying two binomials. Put one along the left side and one along the top. And then just start multiplying. X times 2x will give me 2x squared. 2x times 3 is 6x. X times 5 is 5x, and 5 times 3 is 15. And then we always have to remember to add the diagonal terms because they're both x terms. So those two together give us 11x, and then we have the 15. For number 2, match each quadratic expression that is written as a product with an equivalent expression that is expanded. So if we start expanding this using distribution, we have x squared plus 6x plus 2x and then plus 12. And we have to remember to add these middle terms. Those are like the diagonal on the diagram method. And so we get 8x, and so number 1, letter A there is going to be matched with number 4. For letter B, I'm going to use distribution again. 2x times x gives me 2x squared. 2x times 2 gives me 4x. 8 times x gives me 8x. And 8 times 2 gives me 16. So combining these middle terms, I get 12x. So I have 2x squared plus 12x plus 16. So B gets matched with number 3 there. Letter C, I'm going to multiply using distribution again. I have x times x, which is x squared. X times 4, which is 4x. 8 times x, which is 8x. And 8 times 4, which is 32. And again, I have to remember to combine my middle terms because they're both like terms. They're both x terms. So 4x and 8x gives me 12x. So my answer, the expanded form, would be x squared plus 12x plus 32. So it looks like letter C is matched with number 1, which leaves us with the last one, x plus 2. X times x is 2x squared, or x times 2x. X times 6 is 6x. 2 times 2x is 2x. And 2 times 6 is 12. So just to make sure we're getting this done correctly, we have 2x squared plus 8x plus 12, which is, did I mess up here? Oh yeah, this should be a 4x. Good thing I checked. So I do get 10x when I combine those middle ones, and so that's number 2 in expanded form. Number 3 is an interesting question. We want to select all expressions that are equivalent to x squared plus 4x. Well, if I multiply here, I get x squared, and x times 4, I'm using distributive, I get plus 4x. We could do that using the diagram method with just one row here. So we'd have x here and x plus 4 along here, and that gives us x squared plus 4x. So either way, Be careful with letter B. You can't just square this and then square that. So this is a no. It's not equivalent to x squared plus 4 because you would have to actually multiply x plus 2 by itself. And so when you do that, you'll get x squared here, but then you have plus the 2x. And then when you distribute the 2, you'll get another 2x. And then there you get your 4, but now you combine these two middle terms and you do have x squared plus 4 then. So this is a no. Same thing's going to happen here. You're going to end up with a bunch of extra terms. X times x is x squared. X times 4 is 4x. X times x is another x squared. And x times 4 is another 4x. So we get 2x squared plus 8x, and that's not the same. That's 2 times what we have up there. Let's see. And then the next one, so this is a no. The next one, let me get rid of some of this so I can use this space over here. So far we just have letter A. The next one, though, shoot, I should have left this. Remember, this factored out or expanded to x squared plus 4x plus 4. And so if I rewrite this, that's just that. So I'm going to have x squared plus 4x plus 4, and then subtract 4. Those two go to 0, and I do end up with an equivalent expression to that. And then this one, I'm just multiplying, from the right side, so I do get x squared plus 4x. And so E would be an equivalent expression also. So A, D, and E are all equivalent to x squared plus 4x. Number 4, Tyler drew a diagram to expand this, explain his mistake. So it looks like he got the right answer here. I think we'll give him a green check mark like they do on our Desmos activities. And then x times 3x, that's 3x. But we got to give him a couple red checks here. 5 times 2x is not 7x, and 5 times 3 is not 8. He added. So this should have been 10x, and this should have been 15. So he added when he should have multiplied. And what is the correct expanded form then? So now if we combine these diagonal terms and write the correct constant term, we have 2x squared plus 13x plus 15 then. Lesson 9, we have a few problems here to do. Let's see, not too many, so they'll go quick. The first one, write each quadratic expression in standard form. So in other words, expand these out. We have x squared minus 1x plus 4x, and then minus 4, and then we combine those middle terms, and that gives us x squared plus 3x minus 4. And let's try the other one with a diagram method. I'll put it in a different color also. 2x minus 1 can go along the left. 3x minus 1 can go along the top. 2x times 3x is going to be 6x squared. 2x times negative 1 is negative 2x. Negative 1 times 3x is negative 3x. And negative 1 times negative 1 is a positive 1. And so when we write this out, we want to remember to combine our diagonal terms because those are both x terms. So we get 6x squared minus 5x plus 1 then. Is the expression given in number 2 in standard form? Yes. We generally see it's written x squared minus 6x plus 8. But yeah, that's in standard form. And is the expression equivalent to this? Well, let's see. Let's multiply this out to go from factored form to standard form. We'll multiply x times x, which is x squared, x times negative 2, which is negative 2x, negative 4 times x, which is negative 4x, and then we have plus 8. And when we combine our middle terms, which are both x terms, we do get x squared minus 6x plus 8. So yes, that is equivalent. Number 3, which quadratic expression is written in standard form? That's this one. The rest are all factors. We're multiplying x plus 3 times x. We're multiplying x plus 4 times itself here. And right here, we're doing some multiplication also. Number 4, explain why 3x squared can be said to be in both standard form and factored form. We can write this as 3x squared times 1. So that would be factored form. As long as you've got two factors somewhere, you're in factored form. And we could write it as 3x squared plus 0x plus 0, and that's in standard form. So if it's a monomial like that, you can write it, it's already in both forms. So number 5, Jada dropped her sunglasses from a bridge over a river. Which equation could represent the distance fallen? So this distance fallen is gonna keep increasing. It's not the same as height above the ground. So represent the distance fallen in feet as a function of time t in seconds. So I'm going to go with letter A here. The distance y would be increasing every second squared by 16 feet. Number 6, a football player throws a football, and here's his time height function for that ball. So we're going to select all the statements that are true about this situation. The ball is thrown from ground level. No, this is our initial height, remember. So h of t is h of 0, which is initial height, plus v sub 0 times t, which v sub 0 is initial speed, or velocity, and that is gravity again. Plus, I guess I should fill out this. So it's minus 16t squared, and that right there is gravity. So the ball is thrown from ground level. This would be a no. Football is thrown from 6 feet. Yes, that's our initial height. In the function, negative 16t squared represents the effect of gravity. Sure does, so we'll circle that one also. Letter D, the outputs of h decrease when the value, or decrease then increase. Decrease then increase? No. They're going to increase. As time goes on, the distance thrown, wait, I'm thinking of the one before. Let me think about this. H height decreases, then increases in value. Nope, it's going to increase. The height above the ground is going to increase and then decrease. So this is the opposite of what's going on with that football. Letter E, the function has two zeros that make sense in the situation. No, it's going to have one zero that makes sense, but remember, if it's thrown from a height of 6 feet off the ground, this part of that parabola doesn't make any sense. The only zero that makes sense is this one. So, well, actually, it's going to go up and then come down. It'll reach a maximum height because you're giving it some velocity. You're not just dropping it. So this is a no. Just one of those makes sense. And then the vertex of the graph gives the maximum height, and that's true. So I would say yes on this, or circle this. Just keep it consistent. And that's it. So, oh, no, I guess not. We have a couple more here that we want to take a look at. One more anyway. I don't want to include 8, so I will take that out of your copy. But we should look at this one. The height of rock A is given by the function f, and the height of rock B is given by the function g. So we want to go ahead and graph each of those on Desmos. And so let's go do that now. This is from 9. Okay, so let's see. So we have these two functions. F of t is equal to 4 plus 30t. I'm just going to use x here just to make it a little easier. So I'm just going to go 4 plus 30x minus 16x squared. And then I'm going to do 5 plus 20x minus 16x squared. So there are my two functions, and now I can use these to answer questions about the situation. These are two rocks launched straight up in the air. So it looks like one is launched here at 0, 4. The other one is launched at 5 or 0, 5. This one hits a maximum height of 11.25, and that one hits a maximum height of, let's put all of these points on, and then we can kind of screenshot it and go over and answer the questions. So let's add that in. I'll just cover up this other problem down here. Oh, it's not. Anyway, so let's take a look at this. What is the maximum height of each rock? The maximum height of the first one is 18.063, and which one is that? Rock A. So rock A has a maximum height of 18.063, and rock B has a maximum height of, that blue one over here, 11.25. And then which reaches its maximum height first? Well, you can tell that this one reaches its maximum height 3 seconds after, and this one reaches its maximum height closer to, this is closer to 1, and this must be 0.75 then. So the blue one reaches its maximum height first, so that would be rock B. All right, that's it. So I hope this helped, and we'll see you soon.